Hello students, welcome back. Previously we went through the ideas and visualizations of sampling distributions. What is a sampling distribution? It's a probability distribution of any sample statistic. It can be the sample mean, sample sum, sample range, sample standard deviation. There can be many, but whatever statistic, it'll have a probability distribution, and that is called a sampling distribution. Now, how do you visualize sampling distribution? If you just have one sample, you cannot see it. You just have one sample statistic, which can be used as a point estimate of the population parameter, but that's it. You don't see any probability distribution with just one number. So how do we get a visualization? You get, say, 15 samples or 5,000 samples and things like those. And then you can see some pattern. Each sample is a repetition, and if you take multiple samples, then you have repetitions of repetitions, so it can be confusing. But that's the only way to visualize the sampling distribution. Alright, now let's go to the most important of the bunch, sampling distribution of sample means. Previously, we went through those visualizations kind of in relaxed fashion, just by looking at those pictures and trying to brush up the ideas. But no more of that. This time, you really have to understand thoroughly. Okay, here we go. Roll 4 dice 100 times and record the sum and the average. Sum is blue. The mean we have red. The pictures are deceptively similar. Are they the same? Think about that. The answer is yes, except for scaling. Look at these numbers here and those numbers there. Otherwise the same. What's the difference? Well, this is sum of 4 dice. And then this is mean, so divide by 4 and we get this. So same thing here, divide by 4, we get that. So it's just scaling issue. So look at these numbers here, from 0 to a little bit less than 25. Divide by 4, we get from 0 to a little bit less than 6, obtained by dividing by 4. Now this is for 100 repetitions. Run it again, run it again. Do you see any pattern? Nothing, except blue and red are the same. Now let's go to 1,000 repetitions. Is it better? 10,000 repetitions. Is it better? 100,000 repetitions. Okay, finally. You can clearly see now that you're looking at the normal pictures. Let's go to the next example. Choose 5 integers between 0 and 20 and record sum and the average. So here we have sum and here we have means. Again, same pictures because they differ only by scaling. 5 numbers here, this is a sum. Divide by 5 and we get this. So there's no difference between one and the other, except that we have a scaling of 5. Now repeat it, repeat it, repeat it, repeat it. Any pattern? Not really. I can't see anything, so let's go to 1,000 repetitions. Still nothing. 10,000 repetitions. I can see something now. 100,000 repetitions. And how about 1,000,000 repetitions? I can clearly see now that we have normal pictures. Now, is this always the case for sample distribution of sample means? The answer is yes. Not only that, we can quantify that normal approximation. That's the essence of the central limit theorem. Here we go. Let x1 through xn be a simple random sample with mean mu and a standard deviation sigma. By the way, what is simple random sample? x1 through xn must be independent and identically distributed. Independent, yes, and they're all identical, so they all share the same mean and same standard deviation. Now, sigma is the standard deviation of the individual, x1, x2, x3, and so on. Now, for sufficient large n, we take the sample mean and look at the distribution of sample mean. And the sampling distribution of sample mean can be approximated by a normal distribution of mean mu and the standard deviation of sigma over square root of n. Now, the standard deviation is a little bit confusing here because we use the same term, standard deviation of individual already, and the standard deviation again for the sampling distribution of sample mean. Let's try to avoid this confusion. So people decided to use some other term. They use the term SE, standard error, for the sampling distribution of sample means, or actually any sampling distribution, by the way. So this standard deviation, now we will call it standard error. By the way, you can consider standard error as a little bit more general formula, because if you take n equals to 1, then you have sigma over square root of 1, and that's the same as sigma, and that is just sample of 1, so all these are out, and we have just individual x1. So SC formula is a little bit more general than just standard deviation. This n can be even 1. Anyway, the sampling distribution of sample mean can be approximated by the normal distribution, the normal of mean mu, and standard error sigma over square root of n. One more here. If n becomes really large, then look at the standard error. Square root of n is in denominator, so it goes down to 0. So we have more and more concentration toward the center, and we have smaller and smaller error. For example, if each individual is weather pattern, for example, daily temperature or things like those, then they swing big time. You cannot predict the weather. But for example, if you take the average temperature of the same date, say for example, March 25th, for past 100 years and take the average, now that can be approximated or that can be predicted very, very accurately because we can use the central limit theorem with sigma over square root of n, and square root of n, that's large, so we're talking about small standard error, so we have higher concentration toward the center. So the climate can be predicted very, very accurately, even though each individual weather cannot be predicted at all. So that's another way to understand central limit theorem. Of course, central limit theorem goes much deeper than that, but if you want some kind of analogy, then I think that's a good one. Weather you cannot predict because that's individual, but climate you can predict accurately because that's the average. You have sample mean, and then you have standard error, sigma over square root of n, denominator is getting big. So we have relatively small standard error in the end. Alright, there goes one version of central limit theorem, but we can do more. Whenever you have a normal distribution, you can standardize it through the z formula here, x minus mu over sigma previously, but now standard error, so x minus mu over se. Then the normal distribution becomes the standard normal distribution. Mean 0 and new standard deviation of 1. And this one we can calculate using the normal table. By the way, according to our textbook author, people use this sampling distribution of sampling mean. People use the central limit theorem and use normal approximation for SDSM when n is greater than 30, greater than or equal to 30. But that's for old school. Nowadays, expectation is a little bit higher because nowadays high performance computing has advanced up quite a bit more, so expectation is higher. In my class, when sample size at 100 is more, then we're going to use central limit theorem, and we're going to use null approximation through standard C table. And if n value is less than 50, then we'll try to use alternative method. And between 50 and 100, there's a gray area. Okay, we discussed standard error. And now let's go to an example problem. Okay, here we go. Let x be a discrete random variable with the mass function like this. Okay, we have the mass function here, so it is possible to calculate the expected value mu and the probability standard deviation sigma. All right, and then let's consider sampling distribution of sample mean of 100 repetitions. So let's consider this. So x bar, which is x1 plus x2 plus dot 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 x100 divided by 100. And this will be approximated by the normal distribution of mean mu, which can be calculated from this probability mass function, and the standard error, like this. And sigma value is the probability standard deviation, which can be calculated from this mass function. And square root of n, here in this case, square root of 100. And then this, as a matter of fact, oh no, let me use this. This, as a matter of fact, can be standardized into 0, 1, the standard normal, through z equals to x minus mu over SE. As a matter of fact, I should have said x bar, because you get x bar value from the mean. Okay, and this can get a little bit more too much confusing by putting bars in there. Just x minus mu of sigma would have been okay. Anyway, by this, you can get the standard normal. And that's the idea. Okay, that was the strategy. All right. So mean, you can calculate like this. Multiply, 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 and add them all up. Here we go. That was an easy computation. Now, probability standard deviation. First number minus mu squared, deviation squared. Second number minus mu squared, the second deviation squared. And then the third deviation squared, and so on and so forth, each multiplied with probability. Add them all up. That's the variance. Take the square root, and there you go, the standard deviation of this probability mass function. And then the standardization, x minus mu over SE, and x exceeds 1.2, so we are looking for the probability that x bar, and this is going to be approximated by the probability that z, the normal, the standard normal, and you see, we need the standardization of 1.2. minus mu over SE. And what is SE? Sigma over square root of n. In this case, square root of 100. And then what is mu? Well, it's here. And what is sigma? Well, it's there. So you can calculate all these. Well, indeed, we did our calculation. 81.623. There you go. And then z is greater than that. So, if you draw the normal curve, standard normal curve, then you need to get z less than something to utilize your normal table. So 1 minus of this, that's how you can get your normal table going on. As a matter of fact, it looks like this. 1.20 higher, and standardize it, and then 1.2 minus mu over SE, you're going to get negative 1.62 like this, or higher. But if you look up the normal table, you're going to get this left-hand side. That's why you need 1 minus of this. Well, do I have the table here? Alright. Negative 1.6 is here. And then 81.6, and then O2 column here. So 0.0526. So the probability is gonna be one minus 0.0526, and that is gonna be 0.9474 approximately speaking, if my mental math is correct. Yeah, that's what I got. And compared with mathematics class computation, oh, this is pretty decent. So there goes an application problem using the central limit theorem. And please note that the original probability distribution doesn't have to be anyway close to normal. It can be anything. It can be discrete, whatever. If you can calculate mu and sigma, the mean and the probability standard deviation, then you're good to go. You take x bar, which is the sampling distribution of sample mean, and then whatever the value, you just use the z-score computation to standardize it so that you see the probability of this x, or more precisely speaking, x bar greater than 1.2 can be approximated by probability of standard normal now, and then 1.2 minus mu over SE, or this kind of z-score computation is the key. Okay, so much for the preparation, and we're going to talk about the applications in a separate video. Stay tuned.